Now let's talk about calculating area in polar coordinates. Well, in order to calculate areas of regions in polar coordinates, one thing that we don't have to do is convert to parametric equations as we did with derivatives. And that's a good thing because, number one, we didn't actually have any sort of real definition of integration with parametric equations. So we're going to come up with a way of integrating in polar coordinate systems. The difference here, we'll use the same basic concept of calculating areas, but with rectangular coordinates, we used rectangles in order to use as our base of approximation. Here we have to change that. We're going to use instead the area of a sector. All right, so let me remind you what a sector is. So from trig or geometry, you may have run into this. And a sector is a portion of a circle. So think of it as a slice of pizza, except everybody calls a slice of pizza a triangle, and it absolutely is not, because then you wouldn't have the part there. That would not be part of your pizza slice. It's a sector. All right. Now, there is, for your sector, some base angle theta, and using that angle theta, we can determine what the area of this sector is, and we can actually do it fairly easily so long as theta is in radians. And that's really a requirement here, okay? So the area of a circle, the entire circle that is, would be pi times its radius squared. Now, the pi in here, it's actually an angle measure, okay? Pi, we know, is an angle measure that's equivalent to 180 degrees. All right, now, if we adjust that angle measure, we can come up with the area of a sector of a circle rather than the entire thing. And you've probably done this in the past simply by doing pi divided by 2 times r squared to get the upper portion or the lower portion of a circle in certain applications in calculus. But in general, if we multiply by theta over 2 pi, so theta is just, I'm just setting up a ratio of what portion of the entire circle out of, the 2 pi radians that are possible. And if we simplify, the pi's cancel out, and so this becomes 1/2 theta r squared. And this would give me the area of some sector of a circle subject to an angle theta. The important thing is this is just a percentage of the circle represented by theta. And in order to do that percentage, we're dividing by 2 pi radians. So everything has to be measured in terms of radians. Okay, and we're going to use that for the basis of our approximation. And let me show you what we will do with that. Okay, so suppose we have some function r of theta that is, actually I'll say r equals f of theta. So the radius of this curve, so we're in polar coordinates, is based off of some function in terms of theta. Now, if we want to come up with the area of a subregion, so let's say we want to have some starting angle measure theta and some ending angle measure theta. So I'll go from alpha up to beta. So essentially it would be alpha is this angle and beta is this angle measure. But I'm not going to have those written there for simplicity. Okay, if I want to figure out what the area of this region is right here. So I've drawn this to where my function kind of looks like a circle, but it doesn't have to be a circle. It could do all kinds of changes and look strange. So what I want to do is estimate what the value of some subregion is based off of a circle. So I want to partition this. So I want to come up with smaller sectors like this. Okay, and so I would have, say, like some angle measure theta 1, some angle measure theta 2, theta 3, theta 4. And between any of these two, and this will go out to like theta n, of course, I have a sector, and I can find the area of that sector. All right, the area of that sector we could define using the formula that we just came up with. So it would be, so the area of the ith subsector, or subregion, whatever you want to call it, that area should be, I'll say area sub I, it's going to be 1/2, and then theta. Okay, hold on, let's see about theta. So I've got theta 2 and theta 3, so which one would I use here? Well, turns out what I'm going to use instead is something more along the lines like delta theta. So the change in theta as we go from one subregion to the next. Similar to how we use delta x back in rectangular coordinates. Delta x was defined by b minus a, the start and end point, or the distance between the start and end point of my subregion, divided by the number of rectangles I wanted to use. In a similar fashion, this is going to be the end angle minus the start angle divided by the number of subsectors that I want to use. All right, so then this will be 1/2 of delta theta times then r squared, so the radius of each subregion. The radius of each subregion comes from the function itself. So it's going to be f evaluated at theta sub I, and then it's going to be squared because of the square in the area of a sector formula. So that would be the area of the ith subsector. So the approximation here, if we add all of these subsectors up, the approximation is going to be the sum from I equals 0 up to n, however many subregions we have, of 1/2 times f of theta sub I squared times delta theta. Then if we let the number of subregions increase to the point where we have an infinite number of subregions, we'll get the actual area trapped between the origin and this curve, and that would then turn into an integral, and the exact area would look like this. Area is 1/2 of the integral from alpha to beta of f of theta squared times d theta. And you can see where each of the different parts comes from. 1/2 is just from the original area of a sector formula. F of theta has to be squared in this case, and that's again because of how we calculate the area of a sector. And then delta theta turns into d theta whenever we take a limit. The trickiest part here, to be honest, is finding the endpoints of integration. And you can use some trigonometry and some solving to come up with those, but a lot of times these graphs loop over themselves many times, and you end up with a whole bunch of possibilities for your endpoints of your interval. I tend to just use the calculator and try and use a graph in order to come up with the endpoints of the subregion. Whatever you choose to do, either one of those methods is fine. But for time savings, I tend to use graphing on the calculator. Okay, so now we know where this formula comes from, let's take a look at how to apply it. So our first example wants us to find the area contained in one petal of the graph of r equals 2 sine 3 theta. Okay, so what's meant by finding the area in one petal of this graph? Well, let's take a look at the graph and see if that helps us understand. So I have a polar graph, which is 2 sine of 3 theta. All right. The window, I think I'll leave that alone. And when I graph it, here's what I get. So it looks kind of like a flower, and that flower has 3 petals. So that's what it means. To find the area in one petal, it just wants me to find the area in one of these 3 petals. Now, to find the area, I would set up an integral, and I do 1/2, I'll just put that on the outside to start with, of my function squared, so 2 sine 3 theta squared d theta. So ultimately, the question is then, what are the endpoints to make this work? Well, there's a couple of ways of doing this. So let's see how much of the curve is drawn from, say, 0 to pi. All right, so if I change my window, it's right now 0 to 2 pi. But there's one thing I want you to see here. If I go from 0 to pi and I graph it, I get the same graph. So here's what's happening. You'd have to really slow down the calculator in order to see it, but it's drawing from 0 to 2 pi the entire graph twice. It's looping over itself. So if you were to integrate from 0 to 2 pi, you'd get double the area you were supposed to. I don't know exactly which graphs will completely draw in pi radians and which ones will draw completely in 2 pi radians. It seems to be an even or odd thing depending on the number of petals in the flowery image, but I don't know for certain on that. So what I generally do is just simply change the values of the window settings until I can get a feel for what's going on. So this was from 0 to pi. Let's see what happens from 0 to pi over 2. Okay, when I graph it, now something has changed. So I'm only seeing half of that graph now. So this whole graph is drawn from 0 to pi. All I'm looking for is the area from one petal. So one thing I could do is take this knowledge and I could go integrate from 0 to pi, but then multiply by 1/3 because there's 3 petals. And then I just divide the result by 3. So that's one way of handling it. Or if I wanted to do it by just seeing which endpoints result in just drawing a petal, I can continue changing this endpoint. It's generally going to be a standard angle measure. So let's try pi over 3. There we go. So 0 to pi over 3 has only drawn the petal shape once fully. So I could then integrate from 0 to pi over 3 in the end. Either way is fine. It doesn't make any difference in the end. So let's see what happens if we work this out now. So we have 1/2. I do need to square out my function. So this would be 4 sine squared of 3 theta d theta, and integrating the square of a trig function we learned how to do earlier in the class. I'll go ahead and bring this constant 4 out. 4 over 2 is 2, so just take care of that. But in order to integrate sine squared, we had to switch and use a trig substitution and write this as 1 minus cosine of double that angle divided by 2. All right, so that was the power reducing formula. And it looks like these factors of 2 will actually just cancel each other out. And when I integrate 1, that's going to give me theta. When I integrate negative cosine 6 theta. So the integral of cosine does not change the positive or negative value, so it's going to stay minus. The multiplier of 6 on the inside is going to have me divide by 6, and then I have sine 6 theta. And then this is integrated from 0 to pi over 3. Okay, real quick. When I am integrating, first off, constants are easy. They just integrate directly to the variable of integration. One thing, and I might have mentioned this already, but when you integrate your basic functions, if it's only off by a constant multiplier, so this is only off from cosine theta by this multiplier of 6 on the angle measure theta, what's going to happen is you can do the u substitution, but it's always going to just change your outer function, leave the inside function alone, but then divide by that factor. So to speed things up, that's a great way of, doing that. If you want to use the u substitution, that's perfectly fine. All right, so now I will plug in the endpoints. So I would have pi over 3 minus 1/6 of sine 6 times pi over 3 would be 6 and 3 cancel to 2, so sine of 2 pi. Then minus, if I plug in 0, it's going to be 0 minus 1/6 sine of 0, because 6 times 0 is still 0. Sine of 0 is 0. Sine of 2 pi is also 0. So this results in pi over 3. Let's look at another example of those. And suppose we want to find the area contained in the graph of r equals 1 minus cosine theta. So this graph, if we take a look at it, let's see here, this would change to 1 minus cosine theta. And it looks like, yeah, that's fine. All right, my Windows settings, I'm going to change my theta max back to 2 pi. And leave everything else the same. All right, so here's my graph. But the question is, did it draw the whole graph from 0 to 2 pi, or did it draw double the graph? So let's change the Windows settings to go from 0 to just pi and see what happens. Okay, so that's only half. So that means the entire graph here, which looks like this, basically, and we want all the area contained within, it gets drawn from 0 to 2 pi. So my area then is going to be 1/2 of the integral from 0 to 2 pi. My function r, which is 1 minus cosine theta, squared d theta. Okay, so let's first multiply out this binomial. And And it would be the square of the first, which is 1, plus 2 times the first times the second, so minus 2 cosine theta, plus the second term squared. Okay? And I could do a little integration to start with now, but one thing that I am going to have to eventually do is change that cosine squared into an equivalent thing using the power reducing formula. So 1 minus 2 cosine theta plus 1 plus cosine of 2 theta, and I think I'll put that in parentheses, so 2 theta all over 2 d theta. Okay, so let's now go through and do some integration. So I have 1/2 times this whole thing. The integral of the first term is just theta. The integral of the second would be -2 sine theta. And then I have a factor of 1/2, which I'm going to pull out, take care of in a moment. The integral of the 1 plus cosine 2 theta. I would have another theta, and then integral of cosine is going to be sine, but I have yet another factor of 1/2 because the 2 theta. So 1/2 sine 2 theta. All right, and then that needs another parentheses, and everything's going to be evaluated between 0 and 2 pi. Okay, might be worthwhile to take a moment and simplify some things first. Let's see what we can do. All right, so first off, I can distribute this 1/2, so that would be plus 1/2 theta plus 1/4 sine 2 theta. Yeah. And theta plus 1/2 theta, that would be the same thing as 3/2 theta. So 1/2 times 3/2 theta minus 2 sine theta plus 1/4 sine of 2 theta. Okay, now this probably looks fairly intimidating, but here's the thing. Sine is always going to be 0 at multiples of 0 and 2 pi, so a lot of these things end up just canceling out to 0 after we plug things in. All right, so when I plug in 2 pi, this is going to be 3/2 times 2 pi minus 2 sine of 2 pi plus 1/4 sine of double of 2 pi, which would be 4 pi. And then I plug in zeros, which sine of 0 is always 0. 3/2 times 0 would be 0, so that whole thing's just going to be 0. In addition, that's 0, and that's 0. So effectively, the only term we have remaining is this first one. These 2's will cancel, so I have 1/2 outside, and then a 3 pi, so it looks like I have 3 pi over 2 in the end.